Um, this is our lesson on interval estimation techniques, and we will do estimation for population mean and population proportion. We have studied previously in our last lesson what is sampling distribution, what is central sampling distribution for sample mean, and we also saw what is point estimator, and then we also had a hint about what is interval estimation. So we have a recap about point estimation first, and then we will go towards interval estimation techniques. So a point estimation is just a single value or single result of the sample statistic. For example, simple mean X bar is a point estimator of the population mean mu. So let us say the average salary per person in a country is like $10,000 per year. Then suppose we calculated this value using a sample observation. So we will assume if the sample mean is $10,000 salary per year, this is the same value, this will be the same value or same result for the whole population. So that means we are representing the whole population average salary using only one result from the sample or one value. So that means there is no confidence interval, there is no assurance, or there is no associated accuracy about the information that we are producing. So that means we want another method of estimation that give us the information about the accuracy of the estimation. At this moment in point estimation, we just get a single value, like this example showing the SAT set score average value for the sample data 550, and we don't know anything about mu cap. So if you remember in previous class, we saw a table which was showing that if the parameter is mu and the point estimator is X bar, then we can say that the point estimator is biased or contains some sample error using X bar minus mu absolute. But this sampling error or bias can only be calculated if we know that the population mean is known to you, then you can calculate this. Otherwise, you cannot calculate this bias value. So because of this reason, we have to have some other way of estimation that is called interval estimation. Even then, there are very famous methods of point estimation. These are There are three main methods at the undergraduate level. These are method of least square estimation. We will have a basic understanding of this method in the regression modeling. We will see maximum likelihood estimation a bit in our class, where we will do mathematics about the statistics course, and therefore we will cover two of this in class, separate class, and one in the regression modeling. So this is a recap. A point estimator is a single realization, whereas a confidence interval shows a lower confidence limit and upper confidence limit, LCL and UCL. And therefore we have a width of the confidence interval, rather a single value. So for a confidence interval, we have this example. Suppose in the set exam, the population population mean means all the students average grade in the set exam. Suppose there are 50,000 students in set exam in the whole world, then this is the confidence interval for those 50,000 students with the help of a sample data, maybe consisting of 500 students out of 50,000. But that means around 1% of the total. So suppose the interval showing 440 score to 560 score. I assume that the average value is 550 for the whole population of 50,000. You see that the confidence interval is 90%, which is showing the lower value and upper value, and the unknown parameter mu, we don't know the actual value of the parameter mu, but it lies inside this red zone. Second thing, if I increase my assurance, I want to be 95% assured that the unknown parameter mu, which is showing the average marks of all 50,000 students in the population, that is 95% means I want more assurance. If I want more assured result, that means I have to increase my interval size. So you see, if I want to be less assured, less accurate, or less confident, then my interval is small. If I want to be more accurate or more assured that the unknown value of the parameter lie in this interval, that means I need to increase the size of the interval. This is the same concept that we have studied in normal distribution. If you remember, it was one standard deviation, mean plus minus one standard deviation, mean plus minus two standard deviation, and mean plus minus three standard deviation. So these results coincide with those results, but we are not talking about that thing because now we are working with central limit theorem. And if we want to be 99% sure, that means I want to be 99% assured that the unknown population mean mu lie within lower limit and upper limit. So if I want to be 99% assured, I have to increase my interval, the size of the interval. So you see, when we increase the confidence, then we have to increase the size of the interval as well. So this is called level of confidence, 90%, 95%, and 99%. You see, if I am 90% assured that the unknown parameter mu lie between these interval values, these values, you see there is a gray region as well away from this red region. If I am 90% sure that my unknown parameter lie inside this red region, then I am 5% sure that the value is outside this red region on the lower side, and 5% assured that the value lies outside this region on the right hand side. Similarly, if I am 95% assured, then 2.5% on the left and 2.5% on the right, the leftover region shows that my confidence interval is below this lower limit and upper limit. But if I increase to 99% or 99.9%, there will be very, very small regions left on the left hand side and right hand side as well. For example, if I want to see the GPA in the class, for example, your class have not 39, it's an example. So suppose your class have 80 students and I want to take a sample of only 10 students randomly, then we can find the sample mean, and using the sample mean, for example, randomly we select 10 people with repetition or without repetition. I think without repetition is the case. 80 combination 10 is the total number of samples. We studied this in last class. So we can find 90%, 95%, and 99% confidence interval for the whole class GPA based on only 10 students data, only from 10 students data. So this is a confidence. So like this diagram showing the red region are your confidence interval, and the leftover is your area where you are not confident. So confidence interval is a range of numbers believed to include an unknown population parameter. You know, in previous class we saw that we may have different population parameters. For example, population mean mu, population variance sigma square, population proportion P, population ratio Q, sorry, population ratio R, or population correlation rho or R, capital R. So in place of using that different notations, I just say theta. Theta is the population parameter, and that parameter is estimated with a confidence interval with lower confidence limit theta cap L and upper confidence limit theta cap U. So that means we are 1 minus the level of measure of confidence is 1 minus alpha. So 1 minus alpha can be 0.90, 0.95, 0.99. And if I multiply it by 100, it will give me 90%, 95%, 99%. We do not try below 90%, and usually we do not have to test above 99%. So these values are suitable values, 90%, 95%, and 99% when we are in the undergraduate studies. So 90% confident, that means 10% not confident, and 95% confident, that means 5% not confident. And similarly, if I am 99% confident, then 1% not confident. So these non-confidence values are called level of significance, and these are used in hypothesis testing in our next lesson. And so these are the examples that shows that I am 95% sure that it will rain tomorrow. Hope so, maybe yes, maybe no. 5% not sure, 95% sure. And similarly, suppose that GDP of growth of a country will be between this interval after the COVID after the COVID era. So that means maybe I am true, 95% or 90% true. Maybe I am wrong. So when we do confidence interval, I have to stop here and then continue the next slide. So that means if